Yeah, so we just want to put information on our Docker image, and with that, what we want to do is to actually serialize our data to something that is ingestible to Docker. So there are several ways of doing this. So we have we have turtle files. We developed a JSON format previously, but what we're doing now is which I think is an easier way of doing this, is if you can open your repo, is that we can actually serialize it to CSV. And what we have here, so remember from our property graph model earlier, we know that our graph has a node serialization and edge serialization. And this is actually how it looks like. So we have a node CSV file, which is, the format is node type. So for example, we have author or gene or label or whatever node type you want to name it, .node.csv. And here's how it looks like. So the required field is ID and label. And then the rest, we considered it as properties. And so the node type here is kind of important. So this is what we're gonna use as the the node type for our ingestion later. Meanwhile, the edge serialization is also the same. So remember, when we say edge, it has a source and then a target. So we just using, so a source is just a source ID, and then the target is the target ID. And then the relation is, you can define also this. For example, I just defined this go BP, and then the rest. So we have source label, target label. This is optional. Resource, link to resource. These are just optional properties for our serialization. So what we're doing here actually is we're converting GMT files from Enricher to CSV files. So this will be our data point here, our data set here. So I'm not sure if you've already been introduced with Enricher, but the idea with Enricher is that you can enter a gene set example, and then if you submit it, it will provide enrichment analysis by finding gene sets that overlap with your input gene set. So it does this by cataloging the information on this different gene sets. So for example, we have this keg. So we have so this is the label or the description of the gene set, and then we have all of these genes that are associated with this label. So this is how it looks like. And what we're going to do now is we're trying to convert this GMT file into the nodes and edges. Okay, so let's start. So okay, so let's just run this. So what we need to do first is that, so remember, we need to figure out an ID for the node. So the node, we have the annotation label, and then we also have the genes. So what we want to do is first find an ID for the genes. So what we can do here is use Antra's gene ID. So this is what we're doing here. So what we're doing here is actually downloading gene information from Antres. So, and then creating a mapper that will allow us to have this sort of lookup for our genes. So this this table, this notebook, I suggest, this will lots of this for this step, it will take a while actually to run it, but yeah, so I guess we have something like this. So once you get gene meta, for example, we put stat3, and then we have the ID, we say the label, and then we also have like the URI from NCBI gene gov.gene, whatever link that is. And I guess I should have, before this, maybe I should have added the CSV file. so that we don't have to run this. But yeah, I'll just go over this. So serialization. Okay, so now we now have a way for like converting gene names to IDs, and then providing like additional information. So now we want to download the GMT files from Enricher. So here, what it does is that it will just so it will check if the file exists, if that library exists already, and then it will download it. If not, and then save it in your file. So once we have this, we can now start the serialization process. So let's start with Go biological process. So we already have a way to convert gene names to gene IDs. Now we want to figure out how to create how to put IDs to the term, to like your gene set term. So here we see an example. Here is our gene set. So this is just one the first gene set in this Go biological process to 2021 GMT file. So we see here, this is the term, and here are the gene sets associated with it. And if we look at it on Neo4j, it actually looks something like this, wherein this is our gene set or gene set term, and then here are the genes that are associated with it. So that's how we visualize it. And we can see here, so we're trying to figure out an ID for this Go term, but we can actually see that it's sort of already in our label already. So we say that this term is associated with this Go term, or with this Go ID. So the easy way of doing this is just using regular expressions to take this ID, and so that we can use it for our serialization. So yeah, for this GMT file, notice that this label already contains a persistent ID that we can use as a node ID. So we can extract it by utilizing this regular expression. So just going it a bit, just explaining a little bit about regular expression. What this does is it's just looking at the patterns of the string and matching it. So an easy way of thinking this is these are grouped regular expression. We say that, so it says that the label is everything is so from this first parenthesis to the last parenthesis, all of this is the label. So that means it's just the whole thing. Next, we say that an ontology ID, we're trying to match any kind of character until we reach the first open parenthesis, which is this one. So note that I'm using backslash here because like parenthesis is a reserved character. So we're saying that when we put backslash here, that means that I'm actually trying to look for a parenthesis instead of using it as a backslash as a special character. So what we're doing is that, yeah, we're trying to match everything.
I got a question.
Yeah.
Couldn't you use two splits and get that Go term out?
Oh yeah, we can also do that. I mean, that's also like another way. So you do two splits, but the yeah, you can do that. You can just split it
split
like
zero, then yep.
Yeah, you can easily also do that. I mean, there's always like a different there's multiple ways of doing this. I just like using regex because you can see here, if I run this, since I already have like label, ontology label, and then the ID, it will easily, if I do this function in Python, that group deck, it will return me a dictionary that has this stuff. And it's much easy, I don't have to like manipulate stuff anymore because it's already, you're just returned like with with a dictionary that contains everything. But yeah, I mean, you can definitely use splits. That will be probably easier. Just split with Go, using split using Go this term, and then just clean up the ending parentheses. So you can do this several ways, and there's actually like an exercise later that you can potentially use. Play around with it if you can try figuring it out. So yeah, you can see here. So what I do is I just use this go term, and then I also add like a URI, just an additional property. So using like the Go ID. And then yeah, so if you run this, you have something that looks like this. So label ID URI, and yeah, so that takes care of the of our term node, right? So we have the gene node that's already checked, and then we have the term node that's already checked. Now let's work with the relationships or the edges. So remember the way we process it. So we get to process the term and gene nodes. So for the edges, an edge exists if a gene is part of a gene set of that term. So that means there's a connection between term 1 and gene 1, and gene 2 and gene 3, and then term 2 and gene 2, gene 4, gene 5. So what we can do is that we can iterate over the GMT file. So we can iterate of all the lines, do some splits so that we can separate the term and the genes, and then resolve our term metadata using this gene set name resolver that we defined here. So this will give us this dictionary, and then we go over all the genes. So for each gene, we're going to resolve the metadata of the gene using the Antwes ID resolver that we had earlier. And then if it's in there, if it's a valid gene, or if it has an ID, then we can we have already resolved that gene metadata. Then we define an edge. So the edge is basically just a source, the relation, and then the target, which is the term ID, relation, and then the gene ID. And then you can add additional information here. I just added like the source label, the target label, and edge properties. This is there's not much of an edge property here, but I just added this in case you want to add some properties in there. And then yeah, so we are basically just iterating it, resolving the IDs for the genes and then the terms, and then defining this source relation target triple for the edges. And then we save it. So we get the .node CSV file, and then the edge CSV file. So here's what it looks like. We define the term node as Go biological process term, and then the relation as Go BP, and then add some resource, and then if you run this, it's going to iterate over the GMT file, and then run it. So I won't run this because it can take a while to actually run. So, but you can play around with this later. So next, so we actually look at how it looks like. So if we look at the file, it actually looks like this. So Go biological process term .nodes.csv actually looks like this. So we have the ID, the label, ontology label, and the URI. And then so next we have the edge DF, or the edge, the Go biological process. Then this is the relationship, and then this is the second the target node, which is gene. So this is how it looks like. Did I run it? Okay. So if you run it, it looks like this. So this is the source ID, relation, and the target ID, and then some miscellaneous information. So yeah, as I mentioned, here's sort of exercise that you can try to play around. You can work around with, you can try using regex. You can also try splits. So this is MGI mammalian phenotype, which is specific, which is just the same. The difference is that it doesn't have a parenthesis, but it also has like this MP in here. So you can try running gene set name resolver, and then try running the whole thing in here. Okay, so that's that. Another example here that I'm going to show is how to use APIs maybe. So, if sometimes we don't have it's not explicit in the ID in the gene term, the IDs. So what we have to do is actually go to an API to actually resolve stuff. So here you can see here KEGG 2021 human, it only has like this description, and then the associated labels or associated genes, but it doesn't have an ID. So what we can do is that KEGG actually has this endpoint, this REST endpoint. So if you look at that, maybe here, it returns you this one, wherein we have like this term and then some ID maybe that we can use. So we can do is that we can download that, or we can request that, and then create this dictionary that will return, or that maps a term with like the respective I don't know, KEGG ID. So here we see that ABC transporter is mapped to this one, and so we can use that to define our gene set name resolver. So KEGG ID, we just map it here, and as a fail safe, I just say that if it's not in here, let's just use the name. You can also alter this, if you don't want stuff that doesn't have an ID, then you can just say that if if name exists, then do this, then if not, then return nothing. So that's it. That's that. Yeah, so you can, if you run this term node KEGG pathway KEGG, and then iterate over the GMT, it will just run it and then also create this node file and this edge file. So you have something that looks like this. All right. Okay, there's a comment. Oh, so an API, basically it's it stands for it's a programming interface, application programming interface. So it's basically a way for getting data from some external source. For example, here KEGG. So we're able to like query it and then fetch data from it programmatically. So this one just returns everything from that KEGG stuff, and then we created library, or rather a dictionary from that from that. And another example here actually is that if you look at this cancer cell line, so for this exercise, so if you look at how it looks like, print GMT0. So you look something like this. We have a cell line in here, and then like the organ in here, or the tissue in here, and then here the associated gene set. So what we can do here, so what I suggested doing here is that we can use Cellosaurus API. So the Cellosaurus API, there's a description in here wherein what you can do is we can actually query the API, and then it will return you something that looks like this. So for example, in here, I'm trying to create a query Cellosaurus with the ID MCF10A. And then so we just want it to be formatted as JSON, and then we say that we want to return I want the ID, or the ID is the identifier name, and then the AC, which is the accession. So if you actually run this, it will return you something that looks like this. So the API will match.
Put it in the browser and then show what you get.
Oh, yeah. Okay. So,
I guess maybe it needs to have an actual, it's good.
So here it is. So what it does is that it matches this identifier. So MCF10A, MCF10A, so it matches it. And then it will return to you the name list, or like the identifier names, and then the accession list, which is CBCL 0598. There are also like different versions of MCF10A, so there are like different it just tries to match this value, and it will return to all of those that contains that term. But then for here, what we want is CVCL0598. We want just like the exact match. And then we were able to, so we want to say that MCF10A has, we will use this ID or this accession number or accession number as the ID for MCF10A. So yeah, that's just how an API works. It's basically just a way for you to communicate with the server with like with the external resource, and you're able to communicate with it programmatically so that you're able to like fetch data, maybe send data. That's a simple way of like looking at APIs. Yeah, was I able to answer it? Okay. So yeah, I mean, yeah, so this is just maybe this is a little bit yeah, okay. So yeah, so you can also try this, if you can play around with it, if you're able to, use this API to be able to get the ID for CCLE cell lines. So you can use that, you can try this, you can try using that and then run this. And last, so we're just creating CSV file for the terms. Now we have gene.csv. So what I was doing previously is that while I was resolving the genes, I'm actually saving all of the genes that we've used with this to this all genes. This is a dictionary. This is an all genes dictionary. So what I'm going to do is just save all of this all genes stuff to a CSV file, which we call gene.nodes.csv, and it actually looks something like gene df is equal to pd.read csv. So csv/gene. It will look something that looks like this. So we have the ID, the label, and then the URI, which is something that I've shown you earlier that the gene resolver function is using. So now you should now have you probably need to update again your repo, because I just pushed the CSV file so that we don't have to generate it from this step. So just do git pull again. So it should download the CSV file, which is what we're going to use to ingest in our node to Neo4j. So the way we do it to try ingesting it is I already created this import.csv function or import.csv Python script. So you just need to go there. So cd src and then run the following. So Python import _csv.py, then /notebooks/csv. And this should take like a few minutes. Yeah, give it, it's just like a minute or two since it's just small.
So now what we're doing is like we're taking the data in the CSV file and we're putting it inside the Neo4j database.
Yes.
We formatting, like all of the last 20 minutes was formatting the data into a way that we can ingest it into the database. And now by running this command, the database now has all of these nodes and links. And once it has all these nodes and links, we can query it. And we can build like a website that visualize like subnetworks that are part of our query, the results of our queries.
Yes, and if you actually look at so if I'm not sure if you're able to like install Neo4j and ingest data, but if you look at localhost 7474 again, you can now see that we have information. So this just have like the go and keg, so and then gene. So if you actually look at it, you have like those information and you have this stuff.